segment today in Unit 10 is all on circles, parts of a circle, line segments that intersect circles, angles on circles. So today we're going to start with lines and line segments that intersect circles. And if you look at the diagram over here, our first word is the word chord. And a chord is a segment point on the circle. Here we have a chord. Their endpoints are on the circle. Notice a radius wouldn't be a chord because only one of its endpoints is on the circle. The next segment we're going to talk about is called a secant. That's right here. A secant has a chord for its middle, but it doesn't just have endpoints on the circle, it extends through the circle. So a secant is a line that intersects a circle in two places. The next one is a tangent. A tangent is a line that intersects the circle in exactly 1 point. And the point of tangency is the point the tangent touches the circle. All right, we all know what a radius is. A radius is a segment from the center to the circle. And the diameter is the longest chord. It goes through the center. The tangent and secant are going to become very important when you hit pre-calc and calculus. All right, tell whether the line, the ray, or the segment is best described as a radius, chord, diameter, secant, or tangent of the circle. So segment AC, right here, AC, is a radius. AB, you can call AB two things. You could call it a chord, but it's best described as the diameter. Because it's a very specific kind of chord. Notice the notation on C of DE, where it's a ray. Well, it can be a segment, it could be a line, or it could be a ray, but DE is the tangent, and B is point of tangency. And for D, it's not a segment over AE, so it's a line, so we would call that the C-tan. If it was AE like this, we'd call it a chord. All right, tangents of a circle. So consider the line L that's tangent to circle C. Imagine if we folded the diagram so that the fold's crease is perpendicular to line L through point P. The crease should pass through point C. So on the diagram, if we were going to sketch our imagined crease, if we folded that circle on top of itself through the center and made sure that the line L, that segment matched up with itself, we'd have this crease. And notice how it said, so that the fold's crease is perpendicular. So what does that tell you about the tangent line? It's going to tell us that CP is perpendicular to line L. And if it's perpendicular, 90-degree angle. And so if we've got a 90-degree angle, we quite possibly have right triangles that we can design. So we want to verify that segment BC down here where it's length 6 is tangent to circle A. Well, if we want to verify that it's tangent, then we'd need to have a 90-degree angle, wouldn't we? So let's write it out. If BC is tangent, then angle ABC would need to equal 90 degrees. And if angle ABC were to equal 90 degrees, then triangle ABC, ABC is a right triangle. What do we do with right triangles? That's right, Pythagorean theorem with SOHCAHTOA. So we want to prove then that triangle ABC is a right triangle. And to do that, since we have all the side lengths, we can use Pythagorean theorem. A squared plus B squared equals C squared. So our question is 6 squared plus 8 squared equal to 10 squared? 36 plus 64 equals 100 squared. Let's write it out. 36 plus 64 equals 100. Is that a true statement? It is, which means that yes. Back to the original question. Is BC tangent to circle A? Yes, because if it were tangent, that would be a right angle. If that were a right angle, that would be a right triangle. And we just proved, or right triangle. We just proved that the triangle is right. This is going to come up a lot. And this is going back to some old algebra. All right, given B is a point of tangency, so we know it's tangent, so we know that triangle ABC is a right triangle. We want to find the radius R of circle C. So this whole length, AC, that whole length is 50 plus R. So we want to know, well, we already know because it is tangent. We already know that A squared or R squared, and that's this R right here, R squared plus 80 squared equals 50 plus R squared. So this is where a lot of you are going to make a mistake. You're forgetting when you FOIL. So let me do this up above here. 50 plus R squared means 50 plus R times 50 R. So notice the pattern when I do this. You can do this on the side of your paper, but 50 times 50 or 50 squared, 2,500. 50R plus 50R, when you FOIL, becomes 100R plus R squared. You can do an area model, but this is going back to some old algebra. So we're looking for the radius. And in each of these kinds of problems, this is the cool thing that's going to happen. We've got R squared plus 8 times 8 is 64, so it's plus 6,400 equals 2,500 plus 100R plus R squared. Notice what happens. The R squares cancel out. So subtracting 2,500 from the 6,400, we're going to get 3,900 equals 100R. Dividing by 100, our radius equals 39. So again, this problem is going to show up on homework, on review, and on your quiz on Friday. Next problem, another property of tangents. So first thing to note, tangent forms perpendicular. If it's tangent, it's perpendicular. If it's not tangent, it's not perpendicular. So that's one of the properties. And here's another one. If two segments from the same exterior point are tangent to a circle, then they are congruent. So here's another definition. Let's see what it says. Two segments from that same exterior point. So down here, if SR and ST are tangent, then those segments are congruent. I'm going to define it today and prove it tomorrow. We're just going to use it. So it says AB and CB are tangent to circle B. Find the value of X. Well, this one should be easy. If they are congruent, we just set them equal to each other. 2x minus 5 equals x plus 15. Subtract x from both sides, add 5 to both sides. X equals 20. Here we go again. X plus 15 equals 2x minus 5. Well, 2x minus 5 equals x plus, oh no, that's the same problem. Silly me. Silly me. Here we go. 3x plus 8 equals 26. 3x plus 8 equals 26. 3x equals 18. X equals 6. And again, 3x plus 6 equals 2x plus 9. Subtract 6 add 2x, x equals 3. So these are the easy type. This problem here, where you're finding the radius, requires you to remember quadratic, or not quadratic formula, but how to FOIL. And then problem A there, verifying, requires you to use Pythagorean theorem. The Pythagorean theorem, FOIL, and then just setting equal. And then another property of tangent. We've got this polygon that's around the outside of a circle. So in our polygon unit, we put the polygon inside the circle. Here we're going to put the polygon around the circle, and we call that a circumscribed polygon. So a circumscribed polygon is a polygon in which each side is tangent. So we've got some examples on the left, circumscribed polygons. So you would know that each one of those line segments was tangent. And not only would you know that each segment is tangent, but you'd also know that this segment equals that segment. You would know this segment equals that segment, and you'd know that this segment equals that segment. Disappearing on me. And then we have polygons that are not circumscribed. So quadrilateral RSTU is circumscribed about circle J. If the perimeter is already known as 18, let's find X. So just looking up here at BUC, U is that exterior point. And we know that all the segments are tangent, which means that UC and UB must equal the same thing. So we know UC is X, which means UB must also be X. Same thing down below. R is the exterior point. The line segments around the circle are tangent, which means RC and RD are congruent. So RC must be 3. SD must be 3. TB must be X. So I look at this and I can write out a whole long number sentence, or I can go, how many X's do I have? Oh, I've got 4. Perimeter 18 equals 4 of those X's plus how many of those 3? 4 of those 3's. We've got 18 equals 4X plus 12. Subtracting 12 from both sides, 4X equals 6 divided by 4 divided by 4. X equals, you can say 3 halves